In this section, we'll talk about paired samples, often called matched pairs. So, for example, we wanted to compare the repair costs of moderately damaged cars at two different garages. So we basically want to see if Garage 1 charges customers less to repair their cars than Garage 2 does. There are two different ways you could do this. The first one is you could do what's called independent samples. Remember, independent samples means they don't affect each other at all. So we can randomly select 10 cars to take to Garage 1 and get cost estimates for the repairs. Then we can randomly select 15 different cars to take to Garage 2 and we can get cost estimates for those repairs. And then we could just compare the results. But what if the cars that we take to Garage 1 just happen to be more severely damaged? Now, hopefully if you're taking random cars, it kind of mitigates this a little bit. If you're taking random samples, it mitigates this, but it's still possible. Okay, so you could just happen to pick a sample where all the cars in Garage 1 happen to be more severely damaged. Then Garage 1 could really be cheaper, but they're going to be charging more because more work needs to be done, so it won't seem like they're cheaper. So perhaps there's a method that works better. Okay. So for this method, called our paired samples or matched pairs, is we could randomly select 10 damaged cars and we could take each car to both garages. So the repair costs for each garage are going to be obtained for the same cars. So you'll know that both garages had the exact same cars, and so any differences that you see are going to be caused by the actual which garage you took it to and not by the differences in which car you took. So any true differences in our repair cost estimates won't be concealed by the possible differences in which car you took. So you can go ahead and try and set up one here. Okay. Let's try this example. What if we want to test two new drugs on patients? If we try independent samples, we could test, say, 40 patients on drug A and 50 patients on drug B and compare the results. But maybe all the patients on drug A just happen to be older, so maybe they don't respond to the drug as well. Then maybe drug B would seem to be working better because it had younger patients, but drug A might in actuality actually be better. But what if you try to give each patient both drugs? So just like we did with the garages. Well, that doesn't actually work because you can't give one person two different drugs because then they interact and you're still not going to get valid results. So one possible solution to this is we could find two similar people that are like the same age, same health, same disease, same, let's see, personal history or health history, genetic history, etc. So things like that. Make them, same gender. Okay. Basically make them as similar as possible. Okay. And then give one drug A and one drug B. This is why we call it matched pairs. So you find a bunch of pairs that are as similar as possible and then you put one in drug A and one in drug B. That way your two different groups should be as similar as possible and any differences should then be caused by the drugs and not just who was in your group. So let's try it with our first example of having repair costs for two different garages. So I sent 7 cars to each garage. At Garage 1, Car 1, the estimate, so all of these are in hundreds of dollars. Okay. So the estimate for Car 1 was $710 at Garage 1. It was $790 at Garage 2. For Car 2, it was $900 at Garage 1 and $101 at Garage 2. Or Car 3 was $1,100 at Garage 1, $1,200 at Garage 2. So far, it seems like Garage 1 is being cheaper, right? Car 4, though, was $890 at Garage 1, $880 at Garage 2. So we kind of get some that are better at Garage 1, some that are better at Garage 2. So what we're going to look for is kind of overall which one is going to be cheaper. The way that we do this is we're going to find the difference at each one. So we'll do 7.1 minus 7.9. So 7.1 minus 7.9 equals negative 0.8. If we do 9 minus 10.1, we get negative 1.1. And as we keep subtracting, we get negative 1.2, 0.1, negative 0.5, negative 0.7, negative 1.4. So it looks like for everything but car 4, my prices were lower at garage 1. So that's, again, making me feel more like garage 1 might be cheaper. But you always ask yourself, well, this was just a sample of 7 cars. These 7 cars, sure, they were cheaper at garage 1. But is that enough evidence to show that garage 1 is always cheaper for all the cars? Or is that just the 7 cars I happen to pick? So would this hold true for our entire population? So that's why we do a hypothesis test. Now in this hypothesis test, notice I did garage 1 minus garage 2. And it's important to keep track of which way you're subtracting. Because we want to know, is garage 1 cheaper? So that means that if I'm going to do garage 1 minus garage 2, if garage 1 is cheaper, these should be small amounts for garage 1, and garage 2 should be big amounts. Okay. So this should give me negative results. Okay, so my differences should be negative. So what we'll actually end up doing is we'll check and we'll say, is the mean of the differences less than 0? Because if garage 1 is cheaper, then we should have negative results. So we'll say, is our mean of our differences less than 0? So what we're going to do is we'll treat these 7 differences as just any normal data set. Okay, so now we don't even have to worry about our original 2 different sets of numbers. We just have this one data set. We can use our megastat to find our summary information as well. So we have our count. That tells me n equals 7. Now, if you want, you could put a little d on here to remind ourselves it's for differences. Doesn't really matter because we'll treat it the same as normal data. Our mean, that's our sample mean. So our sample mean of our differences is negative 0.8. And our sample standard deviation, that would be S, is 0.503. Again, I put D's on to remind myself it's for differences. It doesn't really matter. We don't treat it any differently. Okay. Our normal curve plot, that looks fairly symmetric, or fairly like a straight line. Our box plot looks fairly symmetric. I would say it looks normal enough, which is good because we have a small sample size, so we want it to look normal enough. So now we want to know if there's a difference in our true population mean repair costs between our 2 garages. Because we have paired samples and we found the difference for each pair, we really only have one sample. So again, these differences are now just one absolutely normal set of data. Okay, we really only have one sample, so we don't need new formulas. We just use our one sample t procedures. Okay. So we can find a confidence interval for the mean of the population differences. Okay, so we're looking for the mean of the differences. The mean of the population of differences is equal to the difference in the individual population means. So what I mean by that is, if I was to find the differences like this for every single thing in the population, and I find the average of all of the differences, that's actually equal to the average of garage 1 minus the average of garage 2. So the mean of every single difference would be equal to the mean of garage 1 minus the mean of garage 2. This is usually easier to interpret if we say write it this way, so we'll probably interpret it that way, but really it's just looking at the mean of every single difference. We don't need a new formula. We just find our one sample t confidence interval that we did before, going back to our TI-84. So let's find our 95% confidence interval for the difference in our population means and interpret the interval. So again, we wrote down from up above, our sample size is 7. Oh, oops, when I typed this, I typed that incorrectly. Our sample mean for the differences was negative 0.8. If you get rid of that negative, it'll change your answers quite a bit. And the sample standard deviation is 0.503. So you can go back to your previous sections to look at how to do a confidence interval. But we need on our T84 to go to stats and tests. We want just a t interval. So here it is, number 8, t interval. We want to put in our summary statistics. X bar is negative 0.8. Our sample standard deviation is 0.503. Our sample size is 7. We want a 95% confidence interval. and calculate it. So it's negative 1.265 to negative 0.3348. Okay, so that is our confidence interval. Now, it was originally given to us in hundreds of dollars, so it might be easier to change this back to hundreds of dollars. So this would be negative 126.5 to $33.48. Just because, again, it was given to us in hundreds of dollars, we can change it back to hundreds of dollars. Okay, so what does this mean? Okay. Well, it means we're 95% confident that the mean of our differences is in there. So I could write, we are 95% confident that the average of all the differences would be between, let's see, negative 126.5 and negative 33.48. Now let's make it more interesting for your boss by actually putting this in context. Because remember, we did the mean of our differences should be equal to the mean of garage 1 minus the mean of garage 2. If we got negative results, then that means garage 1 was smaller or less values. Okay, so we are 95% confident that on average, garage 1 cost between 33.48 and 126 less than garage 2. Now that's a very simple way to say it, something that most people would understand and be able to relate to. So we did a confidence interval. We can also do a hypothesis test for it. So we just use again our basic one sample t-test. We're not really going to do anything new. The most interesting thing is our mean will always or usually be equal to 0, because the boring status quo is that our two garages are equal, so then the mean will just be equal to 0. Our t-test statistic, you may or may not remember, but it's usually just x bar minus the mean of the differences, or sorry, minus our hypothesized mean over s over square root of n. Notice it's exactly the same, we just put a d on everything. Notice though that if the mean of our differences is 0, is usually our null hypothesis, we don't have to subtract something because minus 0 is boring, so sometimes we'll just drop that off. So let's conduct a hypothesis test to see if garage 1 charges less than garage 2 for repairs. So check our conditions. We have to have n equal to 30 or normal. And we checked up above, our data looked normal, so we're good there. Alpha, I'll just use alpha equals 0.05. That's always our default if we don't know anything else. For our hypotheses, remember we want garage 1 to be less than garage 2. Okay, so that means if we subtract them, we should be getting negative results. So for our null, we'd say the mean of the differences equals 0. For the alternative, if garage 1 is less than garage 2, when I subtract, I should get negative results. So I'll say the mean of the differences is less than 0. At this point now, I break out my calculator. I'll go to stats, test. I just want a basic one sample t-test. The hypothesized mean is 0. Sample mean is negative 0.8. Sample standard deviation 0.503, n equals 7. Make sure you choose here that our mean is that we have a less than alternative, and you can either draw or calculate. So notice it tells you it did the mean is less than 0. It told you t, our test statistic, equals negative 4.2. So that means here's my test statistic of negative 4.2. This is a less than, so we would have been shading and finding the area to the left, and that area says is 0.0028. So my p-value is 0.0028. So this p-value, 0.0028, is smaller then alpha equals 0.05. Anytime you have a small p-value, you will reject your null hypothesis. And that means we have evidence for our alternative. So we have evidence that the mean, population mean of the differences is less than 0. That's not quite as interesting to your boss, so let's change it back to English form. So we could say something like, we have evidence that the average for garage 1 would be less than the average for garage 2. And this was for all the possible cars we could have taken in. Okay, because again, it's the averages for the population. So in our sample averages was less for garage 1, and now we can say we have evidence that the average for garage 1 will still be less for all of our possible cars. And just as a side remark here, we just tested to see if garage 1 was less than garage 2. Sometimes if you're being more advanced, you might want to test something like, is garage 1 at least $100 less than garage 2? So then if you do garage 1 minus garage 2, you want to see if that's less than $100. Now, since our numbers were given in hundreds of dollars, we would just change that to -1. Oh, let's see, less than -100. Since garage 1 is less. So we could test the mean of the differences as less than -1. But again, usually we'll just compare the difference to 0.